Today I will be talking about how Python is used in data science. Then we'll get on the ACES cluster and we will start practicing with two of our main data structures, and we'll be practicing with visualizing data. I like to start off slow because you never know if you have people who are joining late. So, I'll pick up the pace in a couple minutes. So overview of Python for data science. So data science is mainly different from other sciences in that the volume of data is much larger. And when there's more data, of course, you have to work harder to keep it organized. So the main thing is, how do you keep your data organized in a way that's clear and scalable so that as the volume of data increases, you're not constantly fighting against your own problems that you created. So let's talk about arrays. Numpy arrays are used for a variety of purposes, but most commonly for numbers. And the reason that they are commonly used for numbers is because they support vector style operations. So if you have 1,000 numbers in two arrays and you want to add element by element pairs from each of the two arrays to make a third array with the same length, I call that the vector style or element by element operation. And the syntax for that when you're using NumPy is very simple. You simply use the syntax that you would use if you were operating on an individual number. Except instead of a number, you substitute the name of the array. And NumPy understands you mean do this operation on all the elements of the array. So that reduces the size of your code. Instead of having to write a for loop or some other kind of structure to iterate over the arrays, you just don't have to write that syntax at all. So that's one less chance to have an error in your code. NumPy, of course, is not the only package that's providing support for arrays. We'll also be expanding further on the array concept with the Pandas library. So the first data structure from the Pandas library is called a series. If an array is like a Python list, then a series is like a Python dictionary. The main advantage of the series is that the index does not have to be a geometric sequence of integers. The index of a series can be any data type that could be the index of a Python dictionary. My goodness, I have a lot of notifications. Excuse me for the interruption. So, a common example of a data type that you would want to use as the index of your data array is time types. So if you're gathering data over time, then each moment in time corresponds to one measurement, and you would like to be able to order your measurements in time and space them out on your time axis correctly. And the most natural way to do that, of course, is to keep your time values and your measurements in the same data structure. So series naturally does that. You can extract and operate on your array using the time instead of the integer position in the array. So I will also talk about plotting today. So a plot has many elements. The the two main parts of a plot, I would say, are the you have the space in which data appears, and the data can be represented by markers of various shapes and sizes and styles. So in this example, the markers are circles that are red. And then outside of that space, you have other labels. So the figure can have X and Y axis labels, titles, tick marks, and various other elements. So those are the main things we're going to be doing today. We're going to be doing mainly array, series, and plotting. That was just a quick overview. And what I want you to have is more resources about how to learn Python concepts. And the most important resource is, of course, this very slideshow, because I would like you to be able to follow along. If there's some code that's a bit large and I ask you to type it with me, then I guess that's probably not going to be very relevant because we're going to be working in a notebook. But let's say you want to revisit these slides later. Of course, you can because we post them on our webpage. So if you visit our webpage, you can get a copy of these very slides. We also post knowledge. So most things we know about Python are on our website under the knowledge base. Previous short courses we've taught are on our YouTube channel. And I always recommend the ACES CI links because it's a curated list with excellent quality. Who's ready to get started? Demetrios asks, are NumPy's arrays kind of like lists? Yes, NumPy's arrays are very similar to lists. NumPy arrays can do almost everything lists can do, but there is one restriction. All the elements of a NumPy array must be the same data type. Provided you're willing to comply with that restriction, the benefit of using NumPy arrays is you get access to a lot of useful functions and operators to cleanly manipulate your data. So lists don't really have a lot of built-in functions for manipulating the data. You can do the sum of a list. That's pretty much it. So if you want to do any other kinds of arithmetic or statistics, you want the library. And yes, other than the one restriction, which is all the elements of the NumPy array must be the same data type, it can do everything lists can do. So I will now proceed to instructing everyone to navigate to the ACES portal. The ACES portal will be our platform for our exercises today. Hopefully, you've taken one of our short courses before and you know how to get to the ACES portal. If not, I'm just going to drop the link in the chat. The ACES portal is our graphical web interface to the ACES cluster. It's powered by a technology named Open on Demand, and we at A&M are very active in the Open on Demand community. So we care about the success of the technology as a whole, not just our platform. So when you try to access this website, of course, it is an authenticated website, and you're going to be redirected to the Access CI logon page. The CI logon page, of course, you can pick your identity provider. If you pick Access CI, then it's just a normal username password form, but I like to pick my institution, and then it redirects me again to my institution. So I don't have to know additional passwords. I can continue to use the same very secure authentication method that my institution provides for me. So I recommend you do it that way. But by hook or by crook, you need to be able to log into ACES. And once you have done that, you should be able to return to the portal and see our portal's homepage. So our portal's homepage has a message of the day and a number of menus along the top. The menu we will be using today is the Interactive Apps menu, which has a drop-down item named Jupyter Notebook for Python Training. I do believe that the menu items may be in a slightly different order today. We're constantly tweaking our menu, so it might not be exactly the second item in the menu, but there should be an item named Jupyter Notebook for Python Training. So let me find that. Portal ACES. Since I've already logged in today, I can skip past the authentication step. Let me increase my font size in case you want to read my screen. So in my interactive apps menu, I do have a Jupyter Notebook for Python Training. It happens to be the third item on the menu this time. I assume they're alphabetized. So I go here, and it's a very simple form because I've already hard-coded all of the details that you need to start this notebook. This text box here is just informational. Like you're not allowed to pick a number that isn't 1. You only need 1 core today. We're not doing anything multi-threaded, so just leave it as 1. And then you hit launch. Now I already clicked launch earlier, so my job should be available somewhere. Yes, so my job is running. So after you click launch, you'll see a card like this, and it will change color. I believe I have some screenshots of that. Right, so you click launch, and then it starts with like gray for queued, and then it goes blue for starting, and then green for running. Then you have a connect to Jupyter button. So you need to click the connect to Jupyter button when it appears. It usually takes about 2 minutes. Jupyter Notebook is not the fastest. Okay, so at this stage, we do sometimes have some technical difficulties. It's very common for people to find that the local accounts are not fully set up, so we have to finish setting them up, and then they should work. I do like to at least wait a few minutes to give more people a chance to successfully reach a running notebook. So a running notebook looks like this. If you've ever used a variant of Jupyter before, there are many. Google Colab is a variant of Jupyter. Jupyter Lab, another popular one. You can even run these notebooks in your VS Code if you like. If you've seen one of those before, this will be familiar. We start with a file navigator. We have 2 files we're working with today. Of course, you should pick the first one first. So I'll do that. And here we have the first notebook we're doing today, which is going to be discussing the data structures. I'm going to go back a slide or 2. And we need to make sure that as many people as possible are able to start their notebooks. So if you recently registered, then it does take some time for all of the servers on the cluster to receive the memo about your local account information. So some of the servers, like the portal node, may recognize you, but then the Slurm node that controls the the jobs may not. And the default solution is just wait a minute and hopefully the memo will finish propagating and then it will work correctly. If that is not the case, then we'll have to look deeper. But hopefully it's just the simple problem. I would like, if you don't mind, for you to use the React feature in Zoom. Do we still have that? Reactions. The green check mark, please, is my favorite. The green check mark lasts the longest when you click on it. So the green check mark, if your job has started running, then we can leave those green check marks up until we feel satisfied that we're all ready to proceed. I see a lot of green check marks. That's very encouraging. And indeed, even some of our participants who were having problems have overcome those problems. So that's very encouraging. I feel ready to proceed. If you still need help, don't be afraid to speak up in the chat. So that is the end of the slides, because after this point, the learning will occur in the notebook itself. So I'm clicking over to my notebook. I'm on 150% Zoom. How do you all feel about my screen font size? Are you able to follow with me? I can make it bigger, but in my experience, 150 is usually big enough. Just let me know if you can't read something. So this course, Python for Data Science, I assume that you have some experience with Python, but maybe you've just used Python built-in features like list. So in order to make more progress with science, you need to learn how to extend Python to get more utility than what's built in. And so the concept in Python for extending your Python capabilities is called modules. And we have modules installed on ACES already. So all you have to do is tell Python that you want to use them. And so we have the import statement, and the import statement tells Python that you want to use code that was written by others. And if the module has been installed, then Python will load all of that code into memory and you can use it. So the most popular Python module that people like to use for science, numeric Python, or Numpy for short. So Numpy provides many mathematical features and, more importantly, the array structure that we previewed earlier. So when you want to use NumPy functions, you must execute import NumPy at least once somewhere in your notebook. Usually it's the first thing you do to make sure you get out of the way. Just check, done. So you have to select your cell and run the cell. It doesn't have any output because normally importing modules is a quiet operation. Jupyter will give you a hint that the code was successful. On this case, we have the number 1, which indicates this is the first cell that I ran today. Since I do want to see some kind of output, I have some additional cells here that will definitely produce output. So if you print NumPy, it will tell you the path on disk to where it found this module. It found it in this path, apparently. That's not especially meaningful, but it's a fun fact. The dir function will tell you what features that module provides. And so here's a list of features. It's quite a long list. I don't think we're going to be able to even read a fraction of those today. And the help function, of course, will give you a summary of what the developers think you need to know. So help unpackage NumPy. NumPy provides an array object, fast math operations, linear algebra, other math topics. How to use the documentation, they suggest going to numpy.org. We're not going to read the whole help function, but in general, I want you to understand how to use modules. So I'm giving you some basic tools that you can use to help you understand modules. So after you have imported a module, then its namespace is now registered in your namespace. So that means in order to access its features, you access them through the module's namespace. And so we use the dot notation, which is very similar to the notation for object-oriented things like methods. If you've previously seen methods, for example, lists have methods. These module features use a similar notation. So dot allows you to access a feature that lives within a module's namespace. So here's an example. Pi is a constant, so you can print it. And you access it with numpy.py. Excellent. Now we never have to type that number in again. If you find yourself typing in this number by hand, you've definitely made a mistake. Now, if you don't use the namespace, if you just print pi from your global namespace, that's not a thing that exists, because now when you import a module, it doesn't pollute your global namespace. It puts everything into that module namespace. So if you want to have a variable named pi, you have to create it yourself. Any questions so far about accessing features of modules? Does it make sense yet? If you have used other programming languages, there may be similar concepts that you've seen before. Okay, so printing pi is not that exciting. Let's move on to something a little more complex. Let's learn how to use functions. So NumPy has a log10 function, and your exercise is to discover what it does and then use it to compute the logarithm of a large number. Anybody have any ideas? What's your favorite way of discovering how to use a new function that you've just heard of? If you start typing numpy.log10, it changes color. But this particular Jupyter IDE is not giving me a mouse hover. That's very sad. My favorite IDEs give me a mouse hover. So without access to mouse hover, what kind of options do we have? Well, we previously saw we can use the help function. So let's execute the help function. And that will explain to you how to use the log10 function. So now I can update my code. So I'm going to compute the log10 of x, where x is an array like. Oh, that's fun. What is an array like? Well, later we're going to see how that works, but for right now, a plain number counts as an array like. So you can just put any plain number in there, like 5,000. I picked a random number out of my mind. So now we can compute the log base 10 of 5,000. Okay, so the next exercise, I would like you to compute the sine of pi over 2. If you have been to high school or primary school, then you may have seen the sine of pi over 2. That's one of the easy ones. We know that the answer should be exactly 1. And not even approximately 1. Like up to the precision of your number space, it should be exactly equal to 1. So hopefully NumPy knows that. I would like to give you a minute to do this one on your own. Would anyone like to drop your solution in the Zoom chat so we can compare? Fahesa asks, are we going to have a lunch break? Yes, there will be a lunch break. Akash suggests print numpy.sign numpy.py over 2. I will drop that into my cell and see if it works for me. It does. So NumPy correctly prints that the answer is 1.0. Okay, so we will now continue on. So far, we've learned that NumPy provides functions. NumPy also provides data types. I gave you a hint earlier that time was going to be a topic of the day, and already we can start learning about time. So in general, the time data type is really annoying. And that's because of things like leap years and not all months having the same number of days. And daylight savings time, even things like that. There are so many concepts with time that make it really just impossible for you to manage it on your own. If you're converting units of time by hand, you're making a mistake. You should not be doing that. So we will be using NumPy's representation of time. So there are 2 units of time. Date time 64 is a unit of time that represents a moment in time. So that would be like a date with, up to any precision, hours, minutes, seconds, nanoseconds. And the other unit of time is time delta. So that is an interval, that is an amount of time that elapsed between 2 dates. And so that can be measured in any particular unit, such as seconds, minutes, days. And the mathematical relationship between a date and an interval is that an interval is a subtraction of 2 dates. Delta is the physics character that we use to represent subtraction. So that is why the word delta appears in the data type. Time delta means it is the subtraction of 2 date times. And we can literally do that subtraction using NumPy. So if we construct numpy.datetime64 and provide a string, and that string is the ISO representation of a date, and then we construct another one, then we can do interval equals day 1 minus day 0, and then we can print, what is this interval? What is its type? What is its value? My IDE is very unhappy with me right now for some reason. It's giving me red underlines. But the code actually does work. So what we have here is a class time delta 64, and its value is this huge number of seconds. Dimitrios asks, what is the difference between the NumPy datetime and the datetime module? So the datetime module is used for when you're just dealing with like one date, and you just need to know facts about one date, then that's good enough. But when you're doing data science, you don't just have one date, you have thousands of them. So NumPy needs to be able to extend the capacity of the date time by adding features that are mainly for dealing with large arrays of dates. So datetime 64 is an optimal data format for working with large arrays of dates, doing arithmetic with them. If you're just operating on one date at a time, they have the same features. So here's a similar example. If you can make an interval out of 2 dates, then you can also make a day by adding an interval to another day. So let's say we would like to know what day is it 3 years after day one. So we construct a time interval, which is time delta, and then this isn't exactly 3 years. This is just a large number of days. And then we add the first date, and then we add that large number of days, and we get the second date. So if we have day plus interval, the result is date times 64, and it has a value. And the value can be expressed in this ISO format. Of course, there's more than one way to express a date. And you'll notice that the day of the month value decreased from 10 to 9, and that's because there was a leap year in that interval. So that means NumPy is correctly understanding the distinction between some fixed number of days and how many days are in each specific year. So you have an exercise. I would like you to compute what will be the date and time 1 million hours from now. So NumPy datetime 64 has a cute shortcut. If you provide the string now as its argument, then it uses your system time, and then we can construct an operation where we add an interval to the current time to get a time in the future. Would anyone like to drop your solution in the Zoom chat when it is ready? Okay, Akash has suggested a solution. Let's try Akash's solution and see what comes out. So Akash's solution was 1 million hours equals NumPy time delta. Is this a million? Yes, that's a million. The letter H. And then answer is NumPy date time 64 now plus 1 million hours. And it comes out as a NumPy date time 64 that is a date in the year 2139. So probably very few people who are alive now will be alive in 2139. Most humans don't live that long. So there you go. Were there any questions about this exercise? Okay, so let's do another topic. NumPy has so many features that it can't even expose them all in a single namespace. So NumPy has submodules for grouping some related features together. So there is a numpy.random submodule, and that's where they've decided to put all of the features related to generating random numbers. So here's two. We have a random integer function and a default RNG function that builds a random number generator. So if you just need one random number, randint is fine. But if you're going to be generating random numbers over and over again, maybe you're doing something like a Monte Carlo simulation. Then a generator is a more efficient way to generate a lot of random numbers that you are sure are they're not going to repeat each other. If you use the random integer function and then you use it again, you're not really certain that you're getting two different random numbers. So a generator is the correct way to generate a lot of random numbers over time. Oh, sorry, I got distracted. We need to concentrate on the concept of a submodule. So importing NumPy is not enough. That just gives you NumPy's global namespace. In order to get access to the submodule, you have to import the submodule. Import numpy.random. And it also has features. Not as many, but they are enough. So your exercise is to discover how to use the numpy.random.randint function to create a random integer. So one of the things about integers is that there are infinitely many integers, and most of them are absurdly large. So if you're not interested in an absurdly large integer, then you'll need to be more specific about a range of integers within which you would like your random integer to be selected. So would someone please like to share in the chat, how do you make a random integer in a particular range? Say, not infinity. Dimitrios suggests numpy random randint 1, 10. I wonder what that does. Let's test it. I got a 6, I got a 9, a 7, a 1, also 1, a lot of ones. I'm trying to figure out if it can give me the 10. There's another 9. It's not giving me the 10. I've gotten all the numbers except 10, I think. So I believe what this means is it will give you 1 through 9, but it won't give you 10. Dimitrios, do you agree that that's what this means? Whoops. The help function says that the low number is inclusive and the high number is exclusive. So that is what that means. Okay, and thank you, Perry and Catherine and Fahesa also for sharing your solutions. So we're not going to be doing very much with random numbers today, I don't think. Maybe later. We're more interested in learning about those data types. So we're going to be learning about the two data types, but because they're very similar, we're going to learn about them at the same time. So that means it's time to, I should probably be more specific. We're going to be learning about those two data structures, the array and the series, but because they're very similar, we're going to learn about them at the same time. So that means now is the time to learn about pandas. So pandas is another popular module for scientific code. So we'll import it. You have to execute that once per session. And let's discover the series class and the array class. So the pandas series is a class, and it starts with a capital S. It is a one-dimensional array structure. Numpy provides an array class, which is ND array. The ND stands for n-dimensional, as in it's some number of dimensions. It doesn't have to be one-dimensional. It can be one-dimensional, or it can be three-dimensional, or whatever number you like. So the main point here is that the pandas series is fully compatible with the NumPy ND array if the ND array is one-dimensional. So a series can only represent a one-dimensional array. If a NumPy ND array is also one-dimensional, then it's fully compatible with the pandas series. If I say array, that could mean either of these types. So the first concept is that arrays are like lists. So they are an ordered sequence of values. The values are all the same data type. The indices, if it's a NumPy array, the indices are 0 to n minus 1. If it's a series, the indices are whatever you want. Because the series can have an index that's whatever you want, it has to be able to report what this index is. So the series has an index property and a values property. So you can check the index or the values if you want to. Both series and ND arrays have a D type property that represents the common data type of all the arrays. So it's similar to a class. You might imagine D type is like, it could be class float or class int or class character. But additionally, it contains information about the memory requirement. So how many bits, for example, does this class store in memory? And that makes it different from Python built-in classes, because the Python built-in classes don't store a specified number of bits. They are automatically expanding containers. Arrays data type is not an automatically expanding container. It is a container with a fixed size. So when you create an array, it computes the size so that it can efficiently store all those values in memory. Normally, you don't have to worry about it because it will compute that for you. The reason I bring it up is because it means the D type is not exactly identical to a Python class. So let's learn how to create some arrays. So the classes have constructor functions. A constructor function is just a function with the same name as the class. And there's more than one way to use it. One of the ways to use it is to take an existing data structure as the input, and the constructor function will transform that data structure into its own type. So if we start with a list is a data structure of 3 elements. This list is a data structure with 3 float elements. If we use that as the input to the series constructor function, we will get a series with these 3 values. When you print a series, it will show you both the values and the index, because the index could be different, and it will also show you the D type. In this case, the D type is float 64. That's not exactly the same as float, because in addition to float, we also have the 64, which is the number of bits that this occupies in memory. It calculated 64 is enough bits to store these in memory. I don't really care. I'm just taking a note of it for your information. So now that we have a series object in memory, let's take a look at its properties. So we can print its type, we can print its D type, we can print its values, and we can print its index. So the D type is float 64, the values are 789, and the index is, oh, this fun thing, a range. So if the index is integers, then it doesn't store them all individually. Instead, it just stores the shape of that array. So if it starts at 0 and stops at 3 and steps at 1, that's your normal range function from Python. Everybody heard of the normal range function from Python that has a start, stop, step? So these 3 numbers are all you need to specify a range index of any size. So it's more efficient to store these 3 numbers than it is to store all the integers 0 to a million. So that's how it does that. So your exercise is build a series from a list of characters. So characters are strings of length 1. And that matters because the Python string type is a self-expanding container. The more characters you put, the larger it grows to contain them. But we know that the arrays are not expanding containers. They have a fixed size. So depending on the input, it will compute the size of the container, and that will become fixed. So if you put in one character, then it will compute what is the amount of memory I need to store one character. If you put in larger strings, it will compute the space it needs to store the largest one, and then all of them will definitely fit in memory. But it will not be an expanding container. So once you have a series of string-like objects, they will have a maximum length. This is just some fun fact. All you need to do is do the exercise, build the series, and then print it and make sure it looks like what you expected. Dimitrios is asking, can we not append to arrays? Yes, arrays have append methods. We haven't gotten to the methods yet. We were going to do methods in a bit, but for example, I have example series up here. Let me just add a new code cell. I can concatenate the example series to itself, but I want to append one thing. All right, pandas dot series 11 point, wrong number of parentheses. There we go. Okay, so I think the reason why this doesn't have an append method is because the series can have an index that's not a geometric sequence. If you're working with an ND array, an ND array has an index that's a geometric sequence, which means there's always a next one. But if your index of your series is not a geometric sequence, then the idea of a next one is not well defined. So for example, if your indices were all like strings, then there's no such thing as a next string. So append wouldn't mean anything. Instead, you would use insert. You would insert one like the way you insert into a dictionary. I do think that series can be inserted like a dictionary, but I'm not super confident about that. This one has a range index, so I don't know how to work with range indices. We'll probably see some examples later to help. We'll be learning about growing these data structures later, but in a context where it feels more natural. Just adding a number to a list doesn't feel very natural. So the methods that Pandas offers do make sense in the context where you're likely to see them in the wild. Sorry, I got distracted. Did anybody suggest a solution to this strings? Okay, so I would like to move on to one more topic. We'll be taking a break soon, but I think we can get through one more topic before the break, if you do not mind. So we've learned how to create a sequence. We've learned how to create a series from an existing data structure. We also need to be able to learn to create a series from like those three numbers, the geometric sequence. So a lot of series that we'll be using will be geometric sequences because they're easy. So here's two different functions that Numpy provides for creating those geometric sequences: linspace and arange. They're very similar. They both can make a geometric sequence of numbers, but their arguments are different because they feel more natural in different cases. So linspace has three inputs. It's a start and end and a number of values. So sometimes you want an array with a specific number of values, and you want them to be evenly spaced in some interval. The NumPy linspace feels like the natural way to do that. So if you want numbers between 2 and 3 and you want 11 of them, then that would be the numbers 2, 2.1, 2.2, all the way up to 3.0. I don't know why my IDE is so upset at me today. This is definitely correct syntax. So one thing I need to point out quickly is that if you are counting by, say, 0.1, and you count 10 of them, then you won't be able to reach both 2 and 3. So it's called the fence post problem. If you include both endpoints, then there's one more than the number of steps. So there were 10 steps to get from 2 to 3. That means there are 11 items in the list that contains 2 and 3. A NumPy function always produces a NumPy array. So NumPy linspace produces an array. We can check by printing its type if you like. If you want a series, you can, of course, pass this structure into the series constructor function to get a Pandas series. So now we have 2 to 3, indices 0 through 10. It's the same data, but now we can print the index and the values separately, because that's the main point of series, is that the index is tracked as a separate thing. So the example was linspace, but your exercise will be the other one, arange. So arange also has 3 inputs, but instead of start end how many, it's start end step size. So if you want to fill an interval by taking a given step repeatedly, but you're not sure how many will be in that interval, then arange feels like the more natural way to do it. So you can construct the array values 2.0, 2.1, etc. by using NumPy arange, and you'll just have the step size be 0.1. But there is a slight difference between these two functions that you will discover when you actually try to use it. So please do the exercise and then tell me, how is the result different? Or what did you need to do differently to get the same result? Either way is fine. Either if you do the same thing, why is the result different? Or what do you need to do to get the same result? So they don't have exactly the same properties, and there's a reason for that, and you will discover it. So will you please try the arange exercise and then let me know what you discovered? I'd like to show you what I'm trying to ask you to do. So we previously created a sequential array by putting 2, 3, 11. And I'm asking you to do arange 2, 3, 0.1, which would be the geometric sequence with the same spacing, right? This array is not the same. Previously, when it was 2, 3, 11, it went 2 to 3.0. And now we have 2, 3, 0.1, and it goes from 2 to 2.9, and 3 is not included. So basically the difference between the two is when 3 was an argument of linspace, 3 appears in the output. When 3 is an argument of arange, 3 does not appear in the output. So one of them is inclusive, the other is exclusive. That's the difference between those two functions. Demetrios, yes, thank you for offering your perspective. The step argument and the count arguments are different. And arange does not include stop. So yes, that is the main difference. So which one of these functions will feel more natural for a use case? It depends on what you're doing at that moment. They're just both options. So one more exercise. I'm going to give you the exercise that motivates why we are using NumPy datetime 64 instead of Python's built-in datetime class. Python does have a datetime class. If you've never seen it before, you just go like from datetime, import datetime, and then you can go t equals datetime dot now. I think it's like that. Is that how that's done? Print t. Yeah, so that looks pretty similar, right? But this is only useful if you just want one date time. But what if you don't want one date time? What if you want an array of dates? Like, for example, a geometric sequence of dates. All the dates between this starting date and this ending date separated by a given interval. Like the built-in date time can't do that kind of logic. It doesn't have the geometric sequence logic that we need. It just does one. So that's why we're switching to NumPy datetime. So in order to make a range of dates, you give NumPy arange a starting date and an ending date, right? I guess you could skip this, something like that. Any ideas? What are you thinking about? We know how to make the next one given the first one, right? So that would be taking one step. We know how to take a step. You add an interval, date plus interval. That's your step, right? Are you following my reasoning? I actually forgot what the solution to this exercise is. I'm trying to build it in my mind. Hopefully I don't make a fool out of myself live on the screen. I think in order to have an array of dates, we need a starting date, an ending date, and an interval, which is, of course, the NumPy expression of an interval for a date is the time delta 64 type. What happens, but the step is optional, right? The arange step is optional, so if we just don't include it, then if we just don't include it, then it has to pick a step size. So what would it do? We can find out. Are you curious? So let's say start equals NumPy datetime 64 now and end will be NumPy dot datetime 64. Well, how about if end is just start plus some interval will be a later time. NumPy dot time delta 99 seconds. And then dates will be numpy.arange start to end. And I'm leaving the step argument out because I want to see what it does. Numpy, oh, I just spelled it wrong. It's time delta 64. Okay, so, oh, that's interesting. So I have start is numpy datetime 64 now. End is another one that's 99 seconds later. And then if I ask for all the dates between start and end, it says, oh, that's a whole bunch of dates and they have the unit of seconds. If the dates have a unit of seconds and they're 99 seconds apart, then there should be like 99 of them, something like that. Yes, there are 99 of them. So I could print, say, you know, the 10th one. So the 10th element of the array would have been 10 steps after the start time. So 10 seconds after the start time. Okay, that's interesting. What if I didn't want the step size to be seconds? Well, of course, we have a step size parameter here. We can just put in a time delta, say 4 seconds. My goodness, my IDE is very upset today. Oh, forgot to close my parentheses. And I forgot to spell my function correctly. Okay, so if I say I don't want my step size to be 1 second, but I want my step size to be 4 seconds, then all of these are separated from each other by 4 seconds. And instead of 99 of them, now we have some other number. I didn't count them. Would anyone like to share in the Zoom chat your solution to this exercise? How did you create an array of dates? Did you prefer to use linspace instead? Maybe instead of datetime 64 now, you could have put in a string. If you put in a string, then you can specify a unit. The unit would be implied by whatever you put in the string, right? So Demetrios tried a solution. I'm going to copy Demetrios's solution so we can talk about it. Oops, that's not what I meant to do at all. numpy.arange. I'm going to go ahead and space this out so I can read it. So this is a numpy.arange with 3 arguments. So date time of this date, and this date will have a unit of day because the smallest part of it is a day. Here's another one that's also a day, and your time delta is 2 days. So it will take 2-day increments from this day to this day. 1, 3, 5, 7, 9. And that's what it did. Excellent work, Demetrios. Thank you for sharing the example with us. Okay, then we will finish learning about the ways to make the series and arrays by learning about making random arrays. So we previously saw some NumPy random functions for creating one random number. And I said that the benefit of somebody in the chat asked, how is this different than Python's built-in random? And I don't recall if I responded, but essentially it's the same answer I gave for how is date time different than the built-in date time, which is that the NumPy random is better when you're dealing with large arrays of numbers. So we will use the NumPy random.rand, which creates an array of random numbers. Its syntax is similar to the other random functions, but you additionally provide a count, how many random numbers you would like. And then we need to convert that to a Pandas series. Which I suppose means we need to read about the numpy.random.rand function first. So the numpy random function has parameters, and the parameters are how many. So D0 is the length of the first dimension. Since we want a one-dimensional array, we just need one argument. And rand produces values from 0 to 1. So we don't get to pick the size of the random numbers if we're using rand. They're already picked for us. But you can scale up 0 to 1. You can just multiply by a bigger number to make this scale up to the size that you want. Whoopsies, what have I done? Okay, so if we take numpy.random.rand and we want some number of them, like, 14. Those will be 14 numbers between 0 and 1. If you want numbers that aren't between 0 and 1, you just multiply. So maybe I want numbers between 0 and 10. And now we have 14 random numbers between 0 and 10. How do you feel about that? Oh, and we're supposed to convert it to a series. So once you have done both of those steps, please drop your answer in the Zoom chat if you wish to share. That's optional. You don't have to share. I'm just curious to know what you came up with for your solution. Okay, so Akash has suggested this code. So Akash's code produces 100 random numbers that are between 0 and 10. Thank you, Akash, for sharing that solution. Let us move on to the next topic of arrays. So in the overview of today, I stated that one of the advantages of using arrays is that it would simplify the syntax for doing arithmetic operations. NumPy and Pandas arrays both support arithmetic operations element-wise. So here are some operators that we know, some arithmetic operators. We have these, and then the conditional operators, which comparison operators, of course. And if star is my notation for an operator, so one of these, then star array means array, star item, star all the way down. So instead of applying star to the array as a whole, you apply star to each item. So I call that element-wise operations. So an example is array arithmetic. If A is the array 1 through 10, and I print A star 2, and you have to fill in the star because star is not a real Python operator. So you just pick your favorite arithmetic operation and replace the star. So for example, plus. If you run the code, A plus 2 does not mean put 2 onto the array. It means for everything in A, add 2. So it becomes 3 through 12 instead of 1 through 10. And we could try different combinations. So here's the integer division operator. So the integer division is divide by 2, but the result is an integer. So that's what double forward slash means. So half of 1 rounded down is 0. Half of 5 rounded down is 2, and so on all the way up to half of 10 is 5. And so for B and C, I'm showcasing what if they're series instead of arrays? Well, the same properties apply to series. They have element-wise operation. So if the first series is 1 through 10 and the second series is this this particular order of some numbers, I made them not both geometric sequences because then you could, if they're both geometric sequences, then all the operations are kind of the same thing. So this is not a geometric sequence. So if you pick your favorite operator here, like subtract, then the result of subtracting two series is element-wise. So 1 minus 2 is minus 1. And then at the end, 10 minus 1 is 9. No, star is not the same as asterisk, because star is not valid Python syntax, but it is a valid ASCII character. It's I went to my ASCII character table and grabbed star. Maybe it's Unicode. So star is valid Unicode. So I went to my Unicode table and grabbed a star and put it in here. And you can do that. Python variables and operations are normally restricted to ASCII characters, but strings are not. Strings can be Unicode. So the text box as a whole accepts Unicode, and strings accept Unicode. But because if I put the star but it's not in a string, it's not valid, but it at least the text box accepts it. Where was I going with this? Oh yeah, star. So I just go to the internet and I go star Unicode or whatever, and then you grab one of these, go back to your, whoops. I'm trying to copy it. Copy. There we go. Star, star, star. Now I can paste in some stars. So it's just a Unicode character. That's how I usually do that. Would anyone like to let us know which operation you tried that I did not already show in the Zoom chat? When I do B/C, I get an INF. That's an interesting one. Let's try that. B/C. So there's an INF. That's interesting. So if you try to do division on two numbers and the denominator is 0, that would normally be an error in Python. And specifically, it would be a division by 0 exception. But if you have a large array of numbers and one of them is division by 0, you don't want to necessarily crash the entire code. So instead of providing an error, the NumPy uses the float value infinity. Infinity is like a NumPy specific float value. So float 64 here is not exactly the same as the Python class float. The Python class float doesn't have an infinity, but float 64 does. And that is so that if you have a division by 0 error, it just makes that one element not valid rather than ruining your entire array operation. And that will be a common thing that people will be dealing with when doing data science, is some of the elements of your data structure will be messy and you have to learn how to clean them up. And those are the types of things we learn how to deal with. So it's better to clean up on a series that has some infinities than it is to lose your whole work because one of them wasn't right. That's the NumPy philosophy. So let's talk about array comparison. So here's some examples. We can compare array with number. So let's say I would like to know a greater than 5. So then it computes 1 greater than 5, false. 2 greater than 5, false, etc. So now we have an array of Booleans. So the result of an array operation that is a comparison, it would be an array of Booleans. So if we do B equals C, then it will just drop falses except for the ones where they're actually the same, and then you get the trues. And arrays of Booleans are actually very, very useful. We will see, I think we will see later why I say that. But this is an important thing to understand, is that if you compare two arrays, you get an array of Booleans, and arrays of Booleans are very useful. So let's do some exercises. So we have the test for divisibility. If you recall from your high school or primary school, one way to test for divisibility is to divide, is to try the division, but it's integer division, and see if the integer division would have a remainder. If you took high school in America, there's a concept called a remainder. The remainder is the part of the original number that would be left over if you had the requirement that the division would be an integer. And so then you reduce the original number until division by integer would be possible. So the amount that you needed to take off of the original number to get to a multiple of the divisor would be the remainder. If you didn't go to school in America, it's a weird concept, but it's basically the modulus operator is the amount by which A is greater than a multiple of B. And if A is greater than a multiple of B by the amount 0, then A is a multiple of B. So that's how this expression computes divisibility. So if we have a bunch of numbers and we divide them, and we will get sometimes whole numbers and sometimes not whole numbers. So if you want to predict whether the result will be a whole number, then instead you do this operation. If this is a number and a number, then the result will either be true or false, and that's coming from the comparison. But instead of doing one at a time, we want to do all of them. So you need to finish the code so that we can compute all of the divisibilities between this array and this array. Demetrios is asking about element-wise operations are not possible with Python lists. The closest you can get to an element-wise operation in Python would be a list comprehension. So I will show you what that would look like with list comprehension. If you have a regular list, A equals 1, 2, 3, B equals 4, 5, 6, then you could compute C equals A. I guess I should switch to uppercase here. A test for divisibility with B for A, B in zip A, B, or something like that. So it is possible. Well, I guess it would be more fun if I switched the order of these so that some of them would actually be true. So yes, it is possible with a list comprehension. A A mod B equals 0 for AB in zip AB. Like, it's a bit clunky. Yeah, you have these extra steps. And also it's not optimized because A and B could be any type. So Python is constantly having to type check between every pair of A and B. Is this operation even possible? Whereas with NumPy, because all the A's and B's are guaranteed to be of the same type, it only has to type check the whole array operation, and then it knows all the element-wise operations will follow. So the array is much faster than the list comprehension. How about another exercise? Date arithmetic. So we know that we can create a range of dates, and we know that we can subtract two dates to make an interval. Can we subtract two ranges of dates to make a range of intervals? Or perhaps subtract a common start date from a range of dates to make a range of intervals. So for example, one might say, I'm counting down the days until Christmas. So for every date in a particular month, subtract Christmas. And that will be how many days left until Christmas. And then you'll have an array of days left until Christmas. And it will count down if Christmas is in the future, and it will count up if Christmas is in the past, right? Does that make sense? So please try the exercise for date arithmetic. Demetrios suggests time interval equals end dates minus start date. So you have computed the number of days until the end of the month. So, but the number of days since the end of the month, but since the end of the month is in the future, it's negative. So negative 13, negative 12, counting up to 0. Eventually you would reach the end of the month and it would be 0 days since the end of the month. Thank you, Demetrios, for sharing your solution. So now that we've seen array operations, let's talk about array functions. We previously learned log10 and sine, two mathematical functions provided by NumPy. And while we were reading their help functions, they said they had an argument which would be array-like. And now we can appreciate why. If the argument to a function is array-like, that means the function applies to each element of the array. So numpy.f, and its argument is an array, means array numpy.f on item, then numpy.f on item. So we could compute the sine of all of the items, for example. And here's the example where we compute the sine of the items. So if we have numpy.linspace, we can create a bunch of angles. So angles are just regular numbers that are, around 1 or 3. And then we use numpy.sine to create an array of, say, positions, if you like, from those angles. And I'm using the numpy.print options to make the output pretty, because when you're printing like floating point numbers, it's nice if they visually line up on the page. So that's what I'm doing. The print options just to make sure the numbers visually line up on the page. Otherwise, this is just a normal print statement. The meat and the potato are the numpy linspace and the numpy sine. Here's the sine. Y equals numpy sine x. But x isn't a number, it's an array. So y will also be an array. So x goes from 0 to pi, and y goes from 0 to 1 and then back down to 0. How do you feel about that? Does that seem useful? It seems useful to me. We're going to use it after lunch, actually. We're going to do some plotting, and we're going to plot some sine functions because they're fun to plot. And this is essentially how we're going to do it, just as some foreshadowing for you. So let's do a different NumPy function we haven't done yet, which is the exponential function. So Python has a built-in exponent operator, like x squared, x to the 5. But that is when you want the that is what you use when you want to apply the same exponent to lots of different bases. If you want to apply different exponents to the same base, then you will probably want to use a different method. And so the numpy.exp is short for e to the power of what comes after, but it's more efficient because it doesn't have to check what kind of number is this. It just automatically knows what to do. So let's make an array of large numbers. First, create a series. We're showcasing that it works with both arrays and series. So you create a series of numbers to be x, then compute numpy exponential of x, save that as y, for example, and that will be an array because NumPy outputs arrays, the ND array specifically, and then we have to convert that into a series because we want to get a series back. So series in, series out, if you're using NumPy, you do have the one extra step of converting to series. NumPy does not give you back the same type you gave it, it just always gives back NumPy ND array. Oh no, I made my words ugly. Okay, they're pretty again. Would you please take a moment to solve this and then let me know in the Zoom when you are done with that? Okay, so Akash modified the previous code. That's a clever strategy, Akash. Akash modified the previous code so that it would use the print options for pretty. And it's not quite as beautiful because those print options were designed for numbers that would be at most 1 digit in the part of the number greater than 1 would be at most 1 digit. So these print options aren't optimal, but they are still okay. And so as a result, now we have large numbers from 1 to 23. How fun. So the exponential of 0 is 1. The exponential of pi is about 23. That's a fun fact. Thank you for sharing, Akash. So we have a bit more time before lunch. I think it would be reasonable to say we could continue doing this optional content until lunch and then go to the plotting notebook after lunch. I don't think it makes a lot of sense to do plotting before lunch because there's not enough time before lunch to learn something really very new. So we should save that new topic until after lunch. Therefore, let us continue with this notebook and do some optional content. The optional content is here in case we have a varying amount of time to spend, which will, I can never quite predict how long everything takes on any given day. Let's learn a NumPy function that is useful when specifically working with date times. Oh, I see that there's a slight issue here. The optional content relies on a concept that we didn't cover yet. I think we have enough time to cover the optional topic, the topic that I didn't cover yet. Slicing. So we'll just do slicing in NumPy, right? So if you had a list, I'm going to create some cells here. If we had a list, um, 1, 2, 3, 4, and we wish to extract a subset of the list, one way we could do it is by providing a slice. So a slice is an index notation where you provide a starting index and an ending index. And like the range functions, the ending index would not be included. So hopefully you've all seen this before. This is just normal list index slice behavior, right? 1, 2, 3, 4. Now, NumPy arrays can also do this. So if we take the same concept, but we make it a numpy.nd array instead of a regular list, and also we remember to put the parentheses in, then it used the wrong function. So as array converts a list to an array. I can't remember what we did before. So if you have a NumPy array or a Pandas series, you can also do slices. They have the same feature. Pandas.series. Yes. So the slice 0 to 2 means get the 0 element, get the 1 element, and then stop. So this is how you slice lists, arrays, and series. Hopefully this is not surprising to anyone because it's exactly the same as before. But arrays and series have something new that lists did not have, which is what's called a mask. So if we take our array A, instead of providing a slice that is in indices, we can provide a list of Booleans the same length to specify whether each element will be included in the subset. So if I put A true, false, false, true, what I mean is I do want the 0 element. I don't want the 1 and 2 elements. I do want the 3 element. And it says no. I think it's because I'm using the wrong notation. I'm going to make A be a NumPy array. So if A is a NumPy array, there we go. Okay. The argument has to also be an array. So to simplify my code a bit, I'm going to put that on its own line. I'm going to give it a name. That is mask. So the mask is an array of Booleans. Okay, the mask is an array of Booleans. I guess a list is fine. I just didn't construct it properly. I apologize for the inconvenience. So a mask is an array of Booleans. The Boolean indicates whether each element will be included in the subset. So if we just want the first and last elements, then the subset A slice, but you put the mask in there, the result will be just the first and last element. And series can also do this, but the syntax is slightly more complex. So I didn't cover it today, but yes, series can also do this. So for now, we'll be focusing on the NumPy arrays. So what is the point of having an array of Booleans and then using that to select your elements? Well, the point is we know how to construct an array of Booleans. So if I go A equals, say A greater than 2, what is that? That is an array of Booleans. Which means that if I go mask equals A greater than 2, and then A mask, I can get the subset of A, but just the ones that are greater than 2. And after you're comfortable with this notation, the next thing you do is you stop naming your mask variable. So you just go A, and then you start speaking like a mathematician. A such that A is greater than 2. And that would be array 3, 4. So instead of saying bracket, I said such that, because now I'm trying to make it make sense in my brain. A such that A greater than 2, array 3 comma 4. So this is an incredibly compact notation to filter arrays. Any questions about using the mask to filter the arrays? The mask is not a specific function. It's just a variable I created. You could name it whatever you want. It's just you take the result of your conditional operation. We know the conditional operation results in an array of Booleans. I just saved it in a variable. The name is not meaningful. We call it a mask because of analogy to paper. If you have two pieces of paper and in one of them you punch holes and then you put that one over the other, you can only see through the holes to the back paper. So the front paper is called the mask. If you put a mask on your face that has eye holes, now someone can see your eyes, but they can't see anything else. So that's what this does. The mask controls which parts of the element you can see, which elements of the original function array you can see in the subset. So now we have the more array functions option. Oh my goodness, what have I done? I just want, okay, so now we have the more array functions optional exercise in which we compute an array of Booleans, which I call the mask. The Booleans indicate which of the dates in the array are business days, so like the opposite of a weekend. Which ones are not on the weekend? So now we can construct an array of dates, construct an array of Booleans, which is for each date, is this a business day? And then we can pick the dates that are business days and print them. So that is your exercise. And the only notation you need to know is dates such that dates, and then you have to fill in the logic, is a business day. You have to actually construct the function call. But, oops, slight typo there. It's supposed to say dates such that dates is a business day. So you can put the logic for which days are business days inside the bracket to get the subset of the dates that match the condition. Oh dear. Well, at least I didn't put the typo. So, okay, so in the chat, I typed dates such that dates is a business day. You have to fill in the logic to compute which dates are business days. Once you know how to do that, you just drop it in the slice bracket to pick out the dates that are business days. I hope you will be able to solve this optional exercise and drop your result in the Zoom chat if you're able to do that. Akash has suggested a solution. Let's see what happens here. Akash, I wonder what is the colon equals operator? I'm not familiar with that one. Does anybody recognize the colon equals operator? Well, let's look at this expression. numpy.isBizDate dates. That is a function that produces Booleans, right? The function starts with the word is, so it should produce Booleans. If it's Booleans, it's already what we need. So I don't think we need this at all. Okay. numpy is business day dates. So that is the dates is business day function call. Dates is the argument. Are these business days? Let's check if there's anything skipped. So the first day is the 17th, and then the next day is the 20th. So the 18th and 19th were skipped, so those must have been the weekend. So now if you're collecting data that's like time series data, but you know the weekends are messed up because like maybe it's financial data and you know that lots of stuff is closed on the weekends, and you're just like, I don't want to deal with weekends. Now you can make sure that your time series data just only includes weekdays. And only 3 minutes left, so I think there's not enough time to do another exercise together. But of course, we do have the last exercise that's available to you if you wish to do it. It just discusses a few different array methods. We won't be needing them today, so it's perfectly fine if you don't feel like doing these right now, but they are worth your time in my opinion. And that means that we will start our lunch break. We will return after the lunch break, and we will do the second of our notebooks, which will be the plotting notebook. Name is Matplotlib plotting.ipymb. If your page is not responsive, you should return to the portal and check that your job is still running. So if you refresh your page and your job is no longer running, you can just make a new one by using the drop-down menu. If your job is still running, you can connect to it and return to what you were doing before. So I have opened the second notebook, Python for Data Scientists, Matplotlib module. Oh dear, it's cold in my office. My fingers are cold. Matplotlib module provides functions for making graphs and drawings. There are many different techniques for making graphs and drawings. You can squiggle your hand on the page. We're going to be focusing on the style where we plot data on a graph. So for that purpose, we have the matplotlib.pyplot submodule, which supports common types of graphs. But that's a lot of letters. So if you have to use a function and you have to type matplotlib.pyplot.function every time, it's going to make your fingers tired. So instead, we're going to give it a nickname using the as keyword. When you import something, you can give it a different name. We'll also be using some Numpy functions. So you need to execute the cell. The cell contains 3 lines. The first is a magic command called matplotlib inline. That's actually not Python syntax. That is a Jupyter Notebook thing. It tells Jupyter Notebook that whenever Matplotlib renders an image, you would like it to display the image in the notebook. That saves you some clicks because instead of having to click to open an image file, it's already happened. The next is import matplotlib.pyplot as PLT. PLT is the most popular nickname for pyplot. And import numpy. So how do we know what PLT is? Well, it has a name property, and we can check that it knows that it's matplotlib.pyplot. So let's make sure that people are following along. If you are with us this afternoon and you're interested in plotting in Jupyter Notebook, then please make sure you can open your notebook and then use the green check reaction in Zoom so that I can determine how many of us are able to proceed, ready to proceed. Okay, so I think that's enough green check marks that I am willing to proceed. Let's talk about the line plot. The line plot is the first kind of plot that everyone should learn. And as a result, they gave it the simplest name. It's the plot function. So the plot function accepts 1 or 2 data objects. If you give it one data object, then it is y data, and you're essentially making a bar plot. The x-axis has no meaning. It's simply a collection of items. If you provide both x and y, then you're giving then the x and y axis will both be scaled numerically, which is what you would expect for a graph. If you provide two objects, then they should be the same length. You can display the plot in the output of the cell using plt.show. But because we have the Matplotlib inline magic, you don't actually have to execute this. It's already the default. So let's look at some basic plotting. I used the word random, but it's not truly random. It's just I put some numbers in a list. These are meaningless numbers in a list. I execute the plot function and then the show function. And an image appears. So now I have the numbers that I put in the list, and they're spaced out along the x-axis in no particularly meaningful way. Matplotlib picked the index of the list 0 to 6 as the scale of the x-axis, which, as you know, the integer indices are not meaningful, so there you go. Oh, and I have a helping function here. Sorry, a helpful cell here. If you didn't put plt.show, then you see the image still appears, but now you have this. This is just the thing that Jupyter normally does, where if the last thing in your cell is an object, Jupyter will tell you what it is. So you can avoid this by just having the last thing in your cell not be an object. It could be an assignment statement, like a equals foo, and then that text is no longer there. And there's many ways to have that text not be there. Okay, so the exercise is a quadratic plot. I would like you to use the plot function to plot a quadratic equation, y equals some arithmetic polynomial of x. And x is going to be an array of data. The easiest way to get an array of data is to use a Numpy function, for example, linspace. So if you have a Numpy array that's data, and then you put it through a polynomial expression, then you'll get a y Numpy array that is the same length, which is perfect because that's what we need, two arrays the same length. So that's how we do it. You create an x array that's just some distribution of points along the x-axis. It's not that important, so linear spacing is fine. And then you put it through the equation to make y, and then you can plot x and y. So if your equation was y equals x squared, you would just use the Python squaring operator, which is asterisk asterisk 2. I would encourage you to choose a more complex polynomial because it's more fun. Would anyone like to share your polynomial in the Zoom chat? Aha, so we do have a submission. Akash, you borrowed some of those print options that we learned earlier. Let's see how it looks like. So you've printed x from 0 to pi, and then some y values that are increasing. Thank you, Akash, for sharing your quadratic with us. Would anyone else like to share? Dimitrios has volunteered to share. Let's see what Dimitrios's plot looks like. Dimitrios, your quadratic goes quite a bit taller. Why is it so much taller? 40,000. Is that because you have larger points along the x-axis? I think it is. Thank you for sharing, Dimitrios. Okay, so now that we know how to plot a quadratic, I would say this is fun. Just typing a math expression. Literally just type a math expression and then plot it. That's just fun. This is why we love NumPy arrays so much. Okay, so let's talk about fancy figures. We know how to put some lines in the chart area, but we need to decorate it. So let's learn some functions for adding more elements to the figure. The plot function has keyword arguments, so you can control the appearance of the lines. The plot submodule also has functions that can add elements to the figure. So you can continue to execute multiple plot functions, plt.function, you can execute multiple functions and they all get added to the same image. And then you hit plt.show whenever you're ready, or if the magic, then it's the default. So you can add a title, a grid, labels and ticks to your X and Y axes. So here's an example of plot customization. Here's a quadratic, y equals x squared. Plot x, y, color equals red, line style equals solid, line width equals 4. Then we execute more plot functions, title, x label, y label. Adding show here is just for completeness. As we know, it is not needed right now. So here's the area of a square, side length versus area. How fancy. So your turn, please customize your quadratic. Go ahead and grab your code from before and paste it down here and then add some more chart elements. I suggest that you could do green dots and triangles, but you don't have to do green dots and triangles. You can find your own color and line style and marker if you want to. I'm sure that Googling a cheat sheet will give you lots of ideas. Let me give you a minute to build your customized figure. Would anyone in the Zoom chat like to share your code that you used to generate a fancy figure? Okay, we have some submissions in the chat. Akash, let's see a fancy figure. We have dash dots, and triangles with black. Quadratic of pi. Thank you, Akash, for sharing your fancy figure. And Sula, thank you for sharing. I would like to view that fancy figure as well. Sula, you have a divide by 0. I wonder why that happened. So you wanted to compute the tangent, right? Oh, the tangent has some vertical asymptotes, right? So if you happen to hit one of those vertical asymptotes, you could get divide by 0. Also, here's another divide by 0. See, you included x equal to 0 in your x data, but then you divide by 0. So I wonder if you didn't mean to have your linspace start a little bit off from 0 somehow. Okay, so the tangent of a small number, and then you cube it. I wonder why some of them are negative. Is only one of them negative? These other ones appear to be positive. So I'm guessing you have a negative number. Sula has modified her expression so that it's even stranger. Okie dokie. I do not know what this plot represents. Dian has submitted a figure. Let's take a look at that one. Season of the year with green dots and triangles. Thank you. And Chelsea has submitted a fancy figure. Purple dashes. Weeks during the semester versus my desire for a vacation. What a very relatable figure. Thank you, Chelsea, for sharing. Okay, so let us move on now to plotting multiple curves. So you can execute the plot function repeatedly within a cell to put multiple curves into the same image. It will look the best, this is just my opinion, if they share a common X data set. In my experience, plots go onto the same image. They look good if they have the same X data set. So we'll create one X data set and we'll use it twice. We'll use it to create two different curves, and then we'll plot two different curves. So you can tell them apart. We give them different color keywords. So here we have two quadratics on the same graph. These quadratics are almost the same. They're only different by a factor of 2. That's why they look that way. You could, of course, make completely different quadratics. So your exercise is to do the trigonometry plot. The famous trigonometry plot is plot sine and cosine on the same image. Very famous trigonometry plot. Everybody has to understand this one to get through primary school, right? So here are some hints. If you use numpy.py in your numpy.linspace function, you can make x values that range over multiples of pi. You're going to need at least a few points in between, because if you just plot 0 and pi, you're not going to see the curves. You need to be plotting like, four or five times that many points at least. Numpy.sine and numpy.cosine can be used to compute your y values from your x values. And here's a bonus for you. You can use LaTeX notation if you've ever done LaTeX. LaTeX is commonly used in physics. I have a background in physics. It's a markup language. If you've heard of Markdown, Markdown is used on GitHub. Markdown is also a markup language. LaTeX is a markup language, and its primary use is for equations. So if you want to have a fancy equation in your title, this is how you do it. $ means equation in LaTeX notation, and then the rest of these characters yield that fancy expression. I will give you a minute to work on that. All right. Akash, thank you for sharing. You really like that print options, don't ya? Oops, that's not the one. There we go. So Akash, the classic sine cosine with LaTeX rendered equations. Okay, so we have sine in green and cosine in yellow. I love it. Uh-oh, we have a typo there. Small typo, Akash. I noticed that it's a bit angular. I wish these were more round. Anybody know what we need to do to make them more round? Go ahead and give your speaking up in the Zoom chat if you know what we need to do to make these look more round. Chelsea has a suggestion. Let's see what Chelsea's suggestion looks like. Chelsea, your suggestion is more round. How did you do that? How did you make these have the appearance of being rounded? Would you please tell us in the Zoom chat? Increase the number of data points. So the only number I see in your code is 130. Is that the number you're referring to? Okay. So 130 turned out to be enough data points. Personally, whenever I'm plotting, when I'm using linspace, I like the number to be odd so that the midpoint is one of the data points. And similarly, I like the number to be a multiple of 5 so that the quartiles are data points. In essence, I like the number to be a multiple of 2 plus 1. The nearest multiple of 2 would be 128. So I probably would have picked 129 as my number of data points rather than 130, because then dividing the plot into subplots would result in data points that are at pretty locations. You can't really see it when there's this many, but let's go back to Akash's plot, which didn't have as many. So you can see that this point here is not exactly at the top, and these 2 points here definitely are not exactly at the bottom. But we can make them that way by making this to be a power of 2 plus 1. So the nearest power of 2 to greater than 10 would be 16, but we have to add 1 because of the fence post problem. Linspace has the fenced post problem. So 17. If you plot with 17, now you'll see that there is a data point at the top, there is a data point at the bottom, and if you could zoom in, there would be a data point right on the axis as well. So that's how I pick those numbers. Why not we move on to the next topic? So we've just learned line plot. Let's learn scatter plot. The scatter plot is almost the same as a line plot. It does have some additional keyword arguments. We're going to cover those in a bit. To start with, the example is you just have some data, you plot it, you get points in a graph. So it's basically the same as the line plot, except I don't see any lines. I just see the markers. Now you can turn the lines off in your line plot. You just set the lines equal to no, or whatever I forget the syntax, but it's not hard to do. You can turn the lines off. So if the question is, if this is just line plot with the lines turned off, why bother, right? The reason is because scatter has some additional fun things it can do. We'll get to that in a minute, but first we need to use scatter to do something where drawing lines would not make sense. So drawing lines makes sense if you're just scanning from left to right on your graph, but not all data is scanned from left to right. Sometimes you have what are called parameterized functions, where the data points are moving around on the graph, but they not always move left to right. They can move right to left, up and down, all possible directions. So when you connect them with lines, the order in which you connect them with lines can cause the lines to cross each other, which is terrible. We do not like the lines to cross each other. So we drop them from the graph and we just focus on the points themselves. So an example is drawing a circle. If you're drawing a circle and you're connecting the points with lines, the lines can cross each other because opposite points on a circle can be connected with a line. Those are both valid points. But so the order in which you draw the points will definitely matter. And we don't have the ability to draw a circle, you don't necessarily know the order in which your data points will arrive. For when you're drawing a circle, yeah, you get to pick the order. But what I'm saying is, let's pretend we don't get to pick the order, because that's going to be the more common situation. So your exercise is to draw a circle using points. You don't know the order the points will land on the circle. So you fill in the circle by just having more points. Does that make sense? I think I talked too much. I'm hoping that someone will understand what I was trying to say and complete the exercise. Anybody want to share your code? Thank you, Akash. Let's take a look at Akash's solution. Akash has drawn... I see. Akash, you made sine and you also made cosine, but this is not the exercise that I was hoping you would do. It says, create a scatter plot that is the sine of your sequence versus the cosine. So x, the sequence itself is not in the plot. The sequence was x. I just want you to plot y1 and y2, but not plot x. Does that make sense? You plot sine versus cosine. The exercise is a little bit contrived, I will grant you that, but what we're learning is valuable. We will learn something valuable from this. Okay, so, aha, I see a green circle. We didn't update the labels. That's not important right now. I'm just trying to understand the circle. So you have drawn a circle. The question is, if you drew these points in one specific order and connected them with lines, you could do it like this, right? So let me show that. If this was a regular plot, then you would have connected them with lines like this. Do you agree? But what if instead of going to 2 pi, what if you went to 20 pi? Oh, I made a mistake. Not 20. How about 21? No, not 21. 19. Okay, I see my mistake. So it's just because that 20 and 21 are coincidentally almost they're related to each other. So if you instead of going to 2 pi, if I went to 19 pi, you can see, well, they're not spaced out the same, but it's still a circle. They're still on the circle. But if this was a line plot, oh no, that's not a circle at all. That's a star. So if you're plotting from 0 to 19 pi, then each angle is a huge jump from the previous one. So your first angle would be 0, and your second angle would be almost all the way around to the other side of the circle, right? You're jumping down here, 0 to, and then all the way down here. So what I'm trying to show is there are some cases where the order in which you draw the points really seriously affects a line plot, but doesn't affect a scatter plot at all. So if you're dealing with data where you're not certain about the order of the data points, a scatter plot is safer. That's one of the lessons I'm trying to make here. Sorry about the contrived nature of the example. Let's just move on. So now that we know what a scatter plot is, let's talk about what we can do with it. So scatter plots have some additional keyword arguments. In addition to setting the color and marker, you can also set properties of each data point individually. So the color and the marker are setting for all the data points, but the C is going to set color for each marker separately, and S sets the size of each marker separately. And since we don't type colors by hand, we usually type numbers. The C map is a rule for translating numbers into colors. And Matplotlib has a bunch of those color maps already built in, so you can pick your favorite if you like. And then we have the same functions we had before for setting other elements of the figure. So here's an example of a colorful bubble chart. So I have 4 different lists of numbers, and then I have a scatter function, and I pass in 2 of the lists as X and Y. I pass in a list for C and a list for S. So I'm setting the color and size of each data point separately. And now we have this. Each data point is a different color and size, totally independent. That can be really useful if you're trying to show complex relationships like categories. Here's some data points that are in this category. Here's some data points that are in this category. Or you can show like measurement intensity. So if you have cities and you're plotting facts about the cities, but also you want to indicate that cities have different populations, you could use the size of the marker to indicate the city's population while you're plotting its other properties so that people's eyes are naturally drawn to the most significant cities because they're larger. So those are the kinds of tricks you can do with bubble charts. So it's your turn to make a bubble chart. How did you tell scatter to show different bubbles? So a bubble chart is just a scatter chart, but each data point has some different properties. So the X and Y data are the first 2 arguments, X, Y. The color for each data point is this C argument, the keyword argument C. So the first bubble, let's say the first bubble is 1, -6. So that will be found right here. That's this one. So the first bubble is located at 1, -6, and its color is 2, and I guess that means purple. And its size is 30, which means it's on the smaller side because these sizes are going up to 90. Is that helping? Was I able to answer your question? Okay. So it's your turn to make a colorful quadratic. You can use your same quadratic formula from before, but I do recommend that you change the constants A and C so that the largest values of Y are at least 200. And that's because if we're going to be setting marker sizes below 100 are not very large. So if you want to see some big marker sizes, we need to get those Y values up there. Is that helpful? So adjust A and C in your polynomial until the largest Y values are over 200. And then scatter plot X, Y, but also set the size keyword and the color keyword with the S and C so that we can make all the points different sizes and colors. And I recommend to you to use the Y values because I told you to make them large as the S values because then the points will be big enough to see. And for X and for the C values, I recommend using X because it actually doesn't matter very much due to the way the C map works. So it's better, but because we already used Y for sizes, why not use X for colors so that we have some variety? Is it at all clear what I'm trying to say? Sorry, it's that time of day where my brain is shutting down and I don't know if I'm making sense or not. And also you need to pick a CMAP uh, option. So on the example, I didn't pick one. The CMAP equals, I don't have that. So that's the default. I don't want you to pick the default. I want you to pick one. So you execute the color maps and it will give you a list. So here are lots of different color maps. I'll tell you some that are my favorite. Uh, I like Magma and Inferno. Those are fun. I like blues. Blues are fun. Um, Cool Warm. That's a fun one I've used before. Viridis. I think Viridis might actually be like the default. I can't remember. Anyways, so just scroll through here till something captures your imagination. Wistia. I saw that's a fun word. I don't know what it means. So after you pick one of those words, you can use it as the value of the CMAP keyword argument and have a very colorful quadratic. I would like to give you some time to do that, and then we will do our break because the last topic is significantly longer. So we're gonna take some more time on that last one. So we'll do the exercise with the colorful quadratic, then we'll take a break, and when we come back, we'll do the last topic. So it's not break time yet. I want you to work on your colorful quadratic. Okay, Chelsea has suggested a solution. Chelsea, I would like to see your solution. It's beautiful. Is it not beautiful? Earth. I see the earth. It's become brown. Akash, I would like to see your solution. It's so colorful. It's like all the primary colors. Oh, because you picked rainbow. I really like this exercise. I don't know, I just when the bubbles change size and color, I just love it so much. Thank you for sharing your beautiful quadratics with me today. We will now go for a 10-minute break. Um, Approximately, let's come back at the 40-minute mark. So that gives us time to finish our exercise if you're still doing it. And what it's like two, so we'll come back at 2:40. Howdy, everyone. Welcome back from your break. We will now proceed to learn the last topic of today, which is an application of everything we've learned so far. We're going to put it all together, and which is why it's so complex. So we're going to learn one new function, which is NumPy's polyfit. NumPy can find the best fit polynomial for some data. On its own, the polyfit function is not so complicated. It's just a function. It takes in some data, it puts out a couple of numbers. But actually putting it to good use is going to be very complex. Now, you might say, but Richard, I can already get a best fit polynomial in like Microsoft Excel, and all I have to do is click a button. Yes, that's true. You can just click a button in Microsoft Excel, and it will do everything that we're about to do for the rest of today. But the button in Microsoft Excel can only handle a few common cases. It can do polynomials, exponentials, that's about it. If you're trying to fit a function that's not one of those, maybe it's a custom function from your weird science field, or maybe it's a machine learning model, then Microsoft Excel can't help you. Whereas if you learn the basic techniques for fitting from today's lesson, they will be applicable going forward as your data gets more complex. So you'll be able to fit more complex functions. You'll be able to fit machine learning models, data with varying kinds of certainty and uncertainty. And obviously, you're in control and it's fully customizable. So the benefit of doing the hard work today of doing a polynomial fit by hand is that all of the pieces will be helpful going forward as you tackle harder problems. Anyway, that's just me on my soapbox. Let's do some learning. So the first kind of polynomial is, so polynomials have degrees, and it's basically the exponent, the biggest exponent you see in the equation. So the first degree that is of interest is the degree 1, which is a linear regression. When the power of x is 1, you're making a line. So what is the best fit line? Well, you can fit any line by tuning the parameters m and b, which are the slope and the intercept. So Numpy polyfit takes your x data and your y data, the value 1, which means you're doing a linear regression, and its output are m and b, the coefficients of the line. So what do we do with m and b? Well, you plot a line, which means you need some x values. So you can use any x values. It is convenient to reuse the same x values that you used for your data. But because of the way plot works, where it connects the lines, and your x data may be in some random order, and when you connect lines in a random order, it doesn't look great. So your data may look better if you sort the x data so that you're connecting lines just left to right. So here's an example, a scatter plot with a linear regression. So I have data 1 and data 2, which are just some numbers from a hat. And then we do Numpy polyfit, data 1, data 2. 1 means it's a linear regression. We save the coefficients m and b. Now we create x for the best fit line, which is just the same x data we had before, but I sort it because if you connect the lines in random order, it doesn't look great. And then we compute y. Since y is a line, it's just mx plus b. How easy is that? Y equals mx plus b. Now we can plot, that's a line plot, the xy data. xy is your best fit line, and we can scatter plot the original data. So you're showing the original data and the best fit line on the same graph. And here we go. So now we have the scatter plot, 1, 2, 3, 4, 5, 6, 7 data points, and a best fit line on the same plot. And okay, yeah, 1, 2, 3, 4 steps to get the best fit line. In Microsoft Excel, 1 step, you click a button. But these 4 steps are, they're teaching you concepts of data science that will be applicable going forward once you get beyond the realm where Excel can do it for you. This what do you call it? The style, the culture, the way of being is what has survived the test of time for being useful. Okay, so that's the example. The exercise is, instead of pulling random numbers out of a hat, you're going to have Numpy create the random numbers for you. Chelsea asks, when you sort x, does it sort y? No, because numpy.sort is a returning function. The original data stays where it is. We're creating a new data. So X is not data one, but you changed data one. Data one is still what it is. X is new. So if you want to sort data one and replace it, you'll have to also sort data two. That's extra work. I don't want to do it. I don't want to. Please don't ask me to do it. I know how. I don't want to. Okay, so create a noisy line. So to make a noisy line, what you do is you start with a normal line, y equals mx plus b, and then to every of the x and y, you add some random numbers. And so then you get a random data that's close to the line, but not exactly on the line. And that's how we're going to make our random data points that we know are close to being a line. So if we follow the steps, we can get two random arrays and add them to x and y to make two data arrays. And then you have to do the linear regression procedure to best fit your x and y data and plot all of those things. And the m and b that are the best fit should be similar to the m and b you originally used to make your noisy line. Oh, the solution is here. Whoops. That was meant to be hidden, but it is not hidden. So perhaps do you want to just like delete that so you can't see it anymore? Goodbye. I can't see the solution anymore because I deleted it. It will take you at least a few minutes to do this. You can ask questions in the Zoom chat. I will help to guide you through this exercise. It is just putting a bunch of things we've done before together with the one new step of get best fit coefficients. And when you have part of a solution, please do share part of a solution so we can talk about it. Okay, Catherine, it looks like you're working on a solution. Do you mind if we take a look? Ooh, colors. How fun. I like the colors. So you have created numbers from 0 to 50. No, numbers from 0 to 15. And then you made a line, which was 3x plus 3. And then you created x and y data by varying x and y by some random amount. And you've printed the best fit. The best fit should be similar to 3, should be similar to 3 and 3, right? But you actually got 3 and 9. Have you noticed it? Okay, the 3 is a very close match. 3.0, almost identical to 3. But then this 9 is a bit different. And then you had some colors, which I really like. Thank you for sharing colors with us. Any hypothesis as to why the best fit B was not equal to the original B you started with? Chelsea, you have a suggestion. Let's take a look. So Chelsea has created a very fancy graph with stars and colors. Thank you for sharing. So likewise, you have a best fit M and B. You did not print them, but I can tell you, because I've done this so many times, that if you were to, you know what I bet it is? I bet it's Grammarly. I bet Grammarly is telling me I'm spelling things wrong. Shoo away, Grammarly. How do you make it not do that? Yes, turn it off. Right, so Catherine, you are onto it. It's because you always were adding a random amount or subtracting a random amount. So it's not, so your data points on average do move a little bit in a specific direction from the line. We could compute what that direction is, but ultimately, if all of your data points are shifting away from the line in the same direction, then the best fit line will slightly be offset from the line that you originally had. The way to correct that problem would be to, when you add a random number, make sure that random number you subtract a little bit so that on average the random number will be 0. Does that make sense? If we go back to your example, you say, okay, we subtracted 3, let's add 1.5. Because on average, sometimes you subtract 3, sometimes you subtract 0. So on average, you're subtracting 1.5. So let's add 1.5. And then when you say, well, let's add 6, let's subtract 3. Because when you're adding random numbers up to 6, on average, you're adding 3, subtract 3. So now on average, you're adding 0. So if we run this code, if you run this code, you get an M and a B that are much closer to your original M and B. They're still randomly different, but they are randomly different, not 9. Now it's close to 3. Why do I feel like when I rerun this, I get the same thing again? I guess there's quite a lot of random element to it. Would anyone like to share anything else before we move on to the end of our session? Yes, Akash has a question. Can we go back and do that optional thing we didn't do earlier? Yes, we can. As I promised to Akash, we can now go back and do the optional array methods exercise that we skipped earlier, if you are interested. Wow. Apparently, I have quite a lot of cell output. I'm just going to clear my cell output. There we go. So here we are, array methods. So there are, broadly speaking, 2 categories of array methods. Some methods return a new array while leaving the old array unchanged. I call these the returning functions. The benefit of the returning methods is that they can be chained together. Since the result of a returning method is an array, it has methods. So you could do array.function. That's called a method chain. And method chains are very popular because they're very readable. You just read from left to right, and the order in which you read is the order in which the operations are evaluated. Now, there are other array methods that are not returning methods. I call these the in-place methods. Some methods alter an array in place. They don't return anything. The variable gets updated everywhere that a reference to it exists. You cannot chain these together. There are very few examples, but when you do see them, you have to be aware of them. Because if you misuse the in-place methods, you get very confused very fast. So here are 2 examples. Array.flatten is a returning method. So here's an array, which is a 2-dimensional array. You can create a 2-dimensional array by passing in a list of lists. And then the flatten method returns a new array, which is a 1-dimensional array. So we'll just print it. Now, array.newArray.sort is not a returning method, it is an in-place method. So after we execute newArray.sort, the same variable will have different contents. It mutates the variable. We can then print the original array, which will still be separate because it is not the same as new array, because flatten makes a new object. So original array is a 2-dimensional array, DCBA. We can flatten it to DCBA, but now 1-dimensional. We can sort it to ABCD. And the original array is not affected because the returning method creates a new object. The old object remains the same. Whereas the in-place method doesn't create a new object. The old object gets the mutation. So that's an example. So your exercise method is to fix a bug. And there's more than one way to fix the bug, of course. But the purpose of this is to use properties of array methods to fix the bug in a way that is very clean. Okay? So what we have here is we want to make an array of integers. And what I've done is I've called the NumPy round method. So the round method, in fact, changes the number. So it takes the number to the nearest whole number by going down. So 2.5 goes down to 2, right? But it doesn't change the type of the data. It's still a float. So it's 2 instead of 2.5, but so this value here, 2.5, will get rounded to 2, but still a float. It will be rounded to 2.0. So if we execute the code, these are whole numbers, but they're floats, 2.0. What I want is whole numbers that are integers. So how can we update the code by adding a little bit more to it in a way that's very clean and readable that removes the bug? What we need to do is execute a method, and we're going to chain the method so that when we round the data, then we convert the data to an integer. But we can do it all in one line. We don't have to create any new variables because a method chain allows you to mutate data more than once without assigning it to a variable yet. So we numpy.round, and then we can continue to activate array methods .as type, and then you can put in any Python type hint. Int is a Python class, so as type will accept it as a type hint. And it doesn't actually do literal int, it does the int64. So it's taking int not as a literal, but as a type hint. You can also put in the actual type you want, numpy int64, I think is how you do that. Or you could put in a different one. You could say, no, I actually wanted int32. But if you don't care about that, you can just use a Python class and it will figure out the intent. But anyway, the point of this exercise was to demonstrate a method chain, which is attaching a method immediately after doing some other NumPy operation. So it's very readable. You round it and then you convert it to int. So the operations happen in the same order as you read left to right. Akash, do you feel satisfied by this exercise? Did anyone else have any questions for me today? Chelsea Bowman has a question. Okay, so if we scroll back up, and we can talk about the business days again. So the first thing we need to understand is this is an array of dates, and the dates include it looks like about 2 weeks worth of days. So like around 4 of them will be on the weekend, right? So what we need to do is we need to compute which of those dates are business days. So we have the isBusinessDays function, which takes as its argument an array of dates, which we have right here, and it returns an array of Booleans, which we'll call the mask. So we'll print the mask. and I'll comment out the rest of this for now. So if the dates are September 17th, 18th, 19th, 2021, then the mask is true, false, false, true, 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 false, false, true, true, true. That's kind of weird. Why do we want a bunch of Booleans that's telling us which ones are business days and which ones are not? The reason that the function is structured in this way instead of in some other way is because an array of Booleans can be used to easily get a subset of the original array. So the original array was dates. So if we do dates mask, then the subset of dates determined by the mask is the dates where mask was true. So we get this one because of true, and then we don't get the next two because of false. So the next one we get is this one. So now we have dates that are business days. And that is because of a feature of Numpy, which is array masking. It's very similar to array slicing in terms of what it looks like on your syntax. You use the brackets, but it's highly extensible. You can even combine multiple masks together. Okay, Chelsea, thank you for your question. How does it know what busy means without creating a business day? I'm not sure I understand your question. So business days are like not the weekends. So this date, this date is its argument. So this particular date on the calendar, we could open up a calendar app and go look at the calendar and determine that this was a Friday. And so internally, NumPy knows how to do that. It knows how to take dates and go look at a calendar and figure out what day of the week it was. And so is biz day just returns true if the day of the week was not Saturday and not Sunday. I'm not entirely certain how dates work under the hood. To be honest, dates are like spooky voodoo magic. If the less you know about them, the better. If you dig really deep into how dates actually work, you're just going to make yourself sad because they're nonsense. They're really actually nonsense. So NumPy knows how to do it. How does it know how to do it? I don't know. Probably it calls some other underlying Python library that calls some other Python library that calls some script written in Fortran from 1980. Like, don't look. You will not be satisfied by the answer. How can we look up these terms that are part of NumPy? So my IDE is not being very helpful today, but normally you would go to NumPy documentation and there's like references and tutorials. Wait, that's not the best one to click on. NumPy user guide. Okay, here we go. So this has all kinds of information. So you can read things you can do with NumPy, things you can do with arrays. There's the API reference. So we could try to find the date time type in here somewhere. I don't remember where it is. It's gonna be here somewhere. I guess we could cheat. So we go to the daytime API, and it says that under the hood, the datetime API was written in the language C. So if you read here, this is not Python code. This is actually C code. Anybody learned C before? Any dinosaurs in the chat like me who know how to program in C? It's a while ago. Right. So NumPy under the hood has this C code, and C code is like not very satisfying to read. And my brain is shutting down. I literally don't think I can answer any more good questions. I hope there's no more good questions because I'm running out of brain power. So Akash, the interactive session. So the notebook itself, it's just in your Scratch directory. So if you go to your Scratch directory, there'll be a folder in here somewhere. Training, yeah, it'll be a training folder, and you can go check out your notebooks. They're just files in your Scratch directory. So as long as you have access to ACES, you can revisit these notebooks. That being said, the allocation, in order to join today's class, you were on our training allocation, and you'll be removed from the training allocation in some number of weeks after we determine, whenever we do cleanup. I don't remember how long, days, weeks. You'll be removed from the training allocation. So if you want to get back on ACES, you'll have to essentially get your own allocation, which is not very difficult to do. You go to the access allocations, and it describes how you get allocations, and some of them are really easy. So like there's different kinds of allocations. There are 4 project types. The smallest one is Explore, and to get an Explore, you can even just be a graduate student. So, and yeah, we serve the Explore level allocations on ACES. So if you're a graduate student, you can get yourself an Explore allocation by just saying, hey, I'm planning to do some graduate research. And then you can trade your credits for ACES credits, hop back on and do this. But that being said, if all you wanted to do was learn Python, you didn't need to use the ACES cluster. There are lots of clusters you could use. You could go to Google Colab and learn Python. So if you're coming to ACES, it should be because we have one of the resources you need to do your research. Lots of people are doing machine learning with GPUs. ACES has GPUs. If you're learning how to use GPUs for machine learning, that's a good reason to be on ACES. You can just make a copy of the notebook right now if you want to go put it somewhere else. Just go file download, get yourself a copy of the notebook. You don't need to come back and to ACES to use the notebook. It's not special. You could open it in your favorite IDE. VS Code will open this. I'm going to share our short course survey. So the survey is this URL or this QR code. They do the same thing. So I'm dropping the link in the Slack in the Zoom chat. The short course survey is how you let us know how we have done and what we can do in the future. So if you need to see more of some things, less of other things, you can let us know and we can change our offering over time to be more relevant to you. That is why it is important to us that you please do fill out our short course survey. All right, everyone, I hope you have a nice afternoon and a nice week. I have run out of brain power for answering questions. I hope you will join us again for a future short course.